All right, so 7.4 is the last section in chapter 7. And what we're doing here is building on what we did in section 7.3. So 7.3, we used the unit circle to expand our definitions of the sine and cosine function so that their domains include all real numbers. Meaning we're not restricted to only plugging in acute angles into those functions, but we can actually plug in any number at all representing an angle. Whether that angle is larger than 90 degrees or pi over 2, whether that angle is 0, negative, or anything you can imagine. So that's incredibly useful because that allows us to use the sine and cosine function for much more than we would have been able to use it for previously. We'd like to be able to do the same thing with our other 4 trig functions. And it turns out that having defined sine and cosine the way that we have now, we can get the other 4 trig functions quite simply just by using the identities that relate them back to sine and cosine. All 4 of the other trigonometric functions relate back to sine and cosine by some identity or another. So here is where we're going to get these definitions. We're going to say that xy is some point on the unit circle determined by some angle theta, just like we did in the previous section. And we showed in that section that our definition for sine of theta is going to be the y-coordinate of this point. The x-coordinate is going to be what we define cosine of theta to be equal to. And now, tangent, cotangent, secant, and cosecant, because all 4 of those have relationships that tie them back to sine and cosine, we can represent all 4 of those in terms of the coordinates of that unit circle as well. So the coordinates of the point on that unit circle. So as an example, remember we established this identity. Tangent of theta is equal to sine of theta over cosine of theta. But if sine is equal to y and cosine is equal to x, this is the same thing as y over x. So that means if we want to find the tangent of theta, and theta determines some point on the unit circle, xy, we can evaluate tangent of theta just by dividing the y-coordinate by the x-coordinate. That's what that says. Cotangent is the only one here that I didn't relate back to sine and cosine, even though I could have. We had an identity that said that cotangent is cosine over sine, but alternatively, it's also the same thing as the reciprocal of tangent. And I just found tangent of theta, it's equal to y over x. Its reciprocal would be x over y. Secant and cosecant, these are the reciprocals of cosine and sine respectively, and so if cosine is x and sine is y, that implies that secant would be 1 over x, cosecant would be 1 over y. Those are the reciprocals of x and y. So let's use an example to kind of illustrate this. Here's a point that does in fact lie on the unit circle. We could verify it by plugging x and y, these 2 coordinates, into the equation that defines the unit circle. X squared plus y squared equals 1. Negative 2/3 squared plus root 5 over 3 squared does equal 1, and you can verify that. But we don't need to do that for this problem. We're just trusting that that point actually is on the unit circle. And we're going to suppose that this point is also determined by some angle theta. Now I could draw a unit circle out and try to locate this point, but that doesn't really help me in any way. I don't need to do that because I have a technique in these 6 definitions here for determining all 6 of my trig functions. For example, what is sine of theta? Well, we define sine of theta, if theta is the angle that determines this point on the unit circle, to be the y-coordinate of that point. So it's literally root 5 over 3. What about cosine of theta? Well, cosine of theta would be the x-coordinate of that point, negative 2/3. That's our definition, right? Now, the other 4 trig functions are combinations of these things. Tangent, for example, tangent of theta, we'd set up here was equal to y over x, or sine over cosine. Now that we know both of those, I can write that as root 5 over 3 divided by negative 2 over 3. The 3's cancel, and I get negative root 5 over 2. Okay, so that's the tangent of theta. Again, I just took the y-coordinate of that point and divided it by the x-coordinate. What about cotangent? Well, I could do x over y, which is how we have cotangent defined up here. Or if I already know what tangent of theta is, we know that cotangent is the reciprocal of this. So this would be negative 2 over root 5. That's the reciprocal of negative root 5 over 2. One important thing to point out here, when you take the reciprocal of a negative number, the answer is still negative. When you take the reciprocal of a positive number, the answer is still positive. That's relevant when we talk about the even and odd identities towards the end of this section. Taking a reciprocal of a number doesn't change the sign of that number. Just mentioning that before we move on. We're not quite done with this one because we do need to rationalize, so I'm going to end up with 2 root 5 over 5 for that answer. 2 more to go. I have, let's do cosecant next. Cosecant of theta. I can either think of as 1 over y, because that's how cosecant of theta is defined here, or I can just think of it as the reciprocal of sine to get the same answer. Sine is what we found over here. Its reciprocal would be 3 over root 5, or after rationalizing, 3 root 5 over 5. Finally, secant of theta is the reciprocal of cosine, which we have over here. That would be negative 3 halves. So all we needed were the coordinates of that point on the unit circle, and all of these were found very easily from that. That's where that definition comes into play, the way that we define these functions. We're going to do another one very similar to that. We're going to find all 6 trigonometric functions, but this time we're not giving the point that's on the unit circle. So I don't know what the x and y coordinates are right off the bat. However, the angle that's being used here is one of those familiar angles that we saw back in section 7.3. In 7.3, remember we had the unit circle at the end of that section with all of these special angles shown and all of the points that they correspond to on the unit circle. We are able to derive that entire unit circle using special right triangles. 5 pi over 4, if you look at your unit circle, is in the 3rd quadrant. And we would see, if we looked at our unit circle, that it corresponds to the point negative root 2 over negative root 2. Okay, and you should go verify that. And in fact, if you didn't have your unit circle in front of you, I said negative and I forgot to write the negative. If you didn't have your unit circle in front of you to kind of, use as a reference, you should actually be able to derive this using reference angles. You should be able to figure out that the reference angle here is pi over 4, drop the perpendicular, do all the stuff that we did in section 7.3. It's just that you eventually want to have this memorized. So that's basically all I have to say about the unit circle. But now that we have this point, we can do this problem the same way we did the previous one. Sine of theta would be the y-coordinate of that point, root 2 over 2. Cosine of theta would be the x-coordinate, which is also negative root 2 over 2. Tangent of theta is sine over cosine. Negative root 2 over 2, negative root 2 over 2. It's the same number divided by itself. That would be 1. Cotangent of theta is the reciprocal of tangent. What's the reciprocal of tangent? Well, the reciprocal of tangent is 1 over 1, which is still equal to 1. So we get the same number in this case. Okay, what about cosecant of theta? It's the reciprocal of sine of theta, which would be negative 2 over root 2. If you rationalize and simplify your answer, you get negative root 2 there, right? Secant of theta would also be the same reciprocal because sine and cosine were equal to each other. So the reciprocals would have to be equal to each other as well. And I know that that would also come out to negative root 2 because of that. Okay? If it feels like I'm moving through this kind of fast, go back and watch through the example again. But because this is essentially the same thing that we did in the previous example, the only new thing was that we had to determine the x and y coordinates of this point with the special angle that we were given. So make sure you're understanding where we're doing both of these. Now, one thing I want to point out here is that in particular quadrants, depending on what quadrant an angle is in, we can predict the sine, not sine S-I-N-E, not the sine function, but the sine S-I-G-N whether something is positive or negative, of one of our trig functions. So notice here, we're in the third quadrant. Sine, cosine, cosecant, and secant, all of those functions gave me negative answers. Tangent and cotangent gave me positive answers, 1 and 1. And it turns out that regardless of what angle we're using, if we're in the third quadrant, that's always going to be true. It's relatively easy to see why that's the case. Every point in the third quadrant, by the definition of the third quadrant, has both a negative x and a negative y coordinate. But if you look up here, if x and y are both negative, then that means sine and cosine will come out negative. Secant and cosecant are the reciprocals of those numbers, and as we stated earlier, the reciprocal of a number does not change its sign. So if the x and the y are already negative, then 1 over x will be negative, and 1 over y will be negative. However, look at tangent and cotangent. Those are defined to be quotients of your coordinates for that point, y over x or x over y. If you take a negative number and divide it by another negative number, you end up with a positive number, and that's why tangent and cotangent are positive. Now, that little pattern that we noticed is not unique to the third quadrant. All 4 quadrants can have similar patterns if we look at them that way. And it's important to be able to recognize in which quadrants are which trigonometric functions positive and in which ones are they negative. So you could derive it every single time, but we have this little mnemonic device, which is really helpful for remembering that. In the first quadrant, all trigonometric functions are positive. So, and we saw that if you go back and look at your unit circle, you'll notice that sine and cosine are both positive in the first quadrant, which is going to make all the other 4 trigonometric functions positive as well. In the second quadrant, sine is positive, but cosine and tangent are negative. And it's not stated here, but we're just going to think in terms of which functions are positive. Tangent is positive in the third quadrant, but sine and cosine are both negative. We saw that in the previous example. Finally, in the fourth quadrant, cosine is positive, while sine and tangent will both come out negative. Okay? So all functions, sine, tangent, cosine. The mnemonic device for remembering that is we take the first letter of each of those words. A, all. S, students. T, take. C, calculus. All students take calculus. It's a way of remembering which functions are positive where. Now, if you notice, none of these functions that are mentioned here reference anything about cosecant, secant, or cotangent, even though those functions will be either positive or negative depending on which quadrant you're in. And the reason for that is because it's enough to know what's happening with sine, cosine, and tangent to be able to determine what's happening with the other 3 functions. For example, if we know that sine is positive in the second quadrant, then cosecant is automatically going to be positive here as well, because cosecant is just the reciprocal of sine, and we know that that doesn't change the sign of that function, meaning it's not going to change it from positive to negative or vice versa. Okay? All students take calculus. That's the way that we want to remember that. All right. We're going to start looking at some new identities. And again, you'll remember from previous videos, identities are a major part of trigonometry. There are tons of them that we cover over the course of this class. And the next ones we want to look at are what are called even and odd functions. So before we look at them from a trigonometric standpoint, we're going to look at them from an algebraic standpoint. And you may have talked about even and odd functions in algebra. But if not, we're going to use function notation here to define this. So given a function f of x whose domain is all real numbers, we say that that function f of x is even, or we call it an even function if this property holds. F of negative x equals f of x for all x. Now that may be you may not be super comfortable with what that means. It may feel a little bit abstract, and I'm going to try and flesh this out for you in a little bit. But let's just remember this definition: f of negative x equals f of x for all x. That part's crucial. Okay, we say that f of x is an odd function if this property holds. Notice it looks very similar to the previous property. F of negative x equals negative f of x for all x. That negative there is the one thing that's different. Okay, so the way I like to describe even and odd functions from just this kind of function standpoint is that if you look at f of negative x, even functions will absorb that negative, and the output will be the same thing as f of positive x. Whereas with odd functions, if I have f of negative x, in an odd function, the negative can be brought out of the function, and it takes the opposite of that output that you would have gotten from f of x. Okay? Still, that might be kind of vague. So let's think about what this means in terms of the graph of a function. That's where these become really the most relevant. The reason we care about even and odd functions is because they exhibit symmetry, which is visible when we graph a function f of x. So down here are examples of very familiar functions from algebra. F of x equals x squared, f of x equals x cubed. This first one, f of x equals x squared, is an even function. And the way I can determine that is if I let x be any real number, then if I were to look at f of negative x, how do we evaluate f of negative x? Well, the literal meaning of this is that we plug negative x in for the x in this function. This is equal to negative x squared. That's what that literally means. Change the x into a negative x. I need parentheses so that I'm squaring the entire thing. Now I know if I square a negative number, it comes out positive. So this is no different from x squared. The squaring kind of kills the negative in that process. But x squared is the same thing as the function f of x, which is defined up here. So this is that property, f of negative x equals f of x for all x. You're seeing that here. It's that property that establishes that this is an even function. Over here, f of x equals x cubed is what we call an odd function, and we verify that the same way. Plug negative x in for your x. That's equal to negative x cubed. But when we have an odd exponents preserve the sign of their inputs, meaning if you take a negative number and cube it, the result will still be negative. So in this case, the negative doesn't get killed off. It stays there. And this is negative x cubed, which is what f of x was defined to be. Notice in this case, it's like the negative came out, and that's how we defined odd functions. So x squared is an even function, x cubed is an odd function. It's not a coincidence that 2 is also an even number and 3 is an odd number, but we don't need to get that deep into this discussion yet. What does the fact that x squared is an even function and x cubed is an odd function imply about the symmetry of the graphs of these functions? Well, even functions are always symmetric about the y-axis. And you can kind of see that from this graph right here. We see that the right-hand side and the left-hand side look like mirror images of each other across that y-axis. And to see how this relates back to the definition, look at these points here. The point 2, 4 and the point negative 2, 4 are both points on this parabola, on this graph, and you can see that they look like mirror images of each other just as points across that y-axis. Well, compare the coordinates of these points. The inputs, 2 and negative 2, are opposites of each other. In the definition of an even function, that's like 2 being x and negative 2 being negative x. These inputs are opposites of each other. Now look at the outputs, 4 and 4. The inputs were opposites of each other, but the outputs were the same number, which is what this is saying. F of negative x would be an output, f of x would be an output, and those two outputs are the same number, 4 in this case. And we can see how that creates that mirror image. I could do that with any pair of points on my parabola where the x coordinates are opposites of each other. The outputs will always be the same number. Okay, so that creates that symmetry about the y-axis. Now, what about odd functions? What do those do? Odd functions have a different kind of symmetry, but it's not symmetry about the x-axis. If you think about it from an algebraic standpoint, no function can have symmetry about the x-axis because that will cause it to fail the vertical line test, and it won't even be a function in the first place. See if you can convince yourself of that. However, odd functions do have a special kind of symmetry that we call symmetry about the origin. So what you see here is a picture or a graph of the function f of x equals x cubed. And looking at it, you can see it does appear to have some kind of symmetry. When we say symmetry about the origin, what we mean is if you take the entire right side of the graph, meaning everything to the right of the y-axis, and then you do two reflections. You start by reflecting that half of the graph across the x-axis, which would put it down here, and then taking that reflection and doing a second reflection across the y-axis. This branch of the graph would flip and overlap with that branch of the graph. That's what we call symmetry about the origin. Compare the coordinates of the points now. Okay, so this time we're using the point 1, 1, which is on the graph, and the point negative 1, negative 1, which is also on the graph. And once again, the inputs are opposites of each other, 1 and negative 1. Only in this case, once they get plugged into the function, the outputs are no longer the same number like they were over here with the even function, but rather the outputs are also opposites of each other. 1 here and negative 1 here. That's what's being described right here. X and negative x are both inputs, but they're opposites of each other. Negative x is the opposite of x. And then the output of f of negative x is the opposite of the output of f of x. That's describing this exact same relationship right here. What that does is creates that symmetry about the origin that we just described. So that's what we really... That's our primary interest when we're talking about even and odd functions. It's the fact that they exhibit this symmetry. Now, we're not going to use that graphical symmetry until chapter 8. However, determining which trigonometric functions are even and which ones are odd, and all 6 of them are one or the other, it turns out. Determining that will help us in some problems when just simply trying to evaluate a trigonometric function at a particular angle. So we'll illustrate that with an example in a minute. But how do we determine which trigonometric functions are even and which ones are odd? The trick is, again, to compare the function at a specific input and then compare that same function to the opposite of that input. So remember, the inputs for trigonometric functions are angles. Let's suppose we want to evaluate or let's define our function f of t to be sine of t. So we're specifically focusing on the sine function, and we want to determine, is sine even or is sine odd? Well, plugging in some angle t, here's the angle t, just sort of some general angle shown on the unit circle. We also need to think about what would happen if we plugged a negative t into our function. That would be sine of negative t. Well, negative t as an angle, we know is the same angle as t, but rotated clockwise from the positive x-axis instead of counterclockwise. And so in this unit circle, we have both t and negative t shown in this circle. And you see this sort of symmetry that's apparent here. What these two angles are doing is they're determining these 2 points on the unit circle, and by the symmetry that would be apparent from this, one point can be thought of as a reflection of the other across the x-axis. What that does is it keeps the x-coordinates of these 2 points the same, x, and the y-coordinates are opposites of each other, y and negative y. That's the key to determining whether sine is an even function or an odd function. So f of t, by definition, is equal to the y-coordinate of that point. So f of t or sine of t is equal to y. What about negative t? Well, looking at the graph, f of negative t would be sine of negative t, which is the sine of this angle, which should correspond to the y-coordinate of this point, making it negative y. Okay, so when I plugged in a negative t, I got the opposite of what I got when I plugged in a positive t. That tells me that sine is an odd function, okay? A similar derivation with cosine, using the fact that the x-coordinates are how we get cosine, and notice the x-coordinate, its sign does not change from this point to this point. That's going to ultimately imply that cosine is an even function, okay? Now, knowing that sine is odd and cosine is even, you can now determine what's happening with the other 4 trig functions. And we're not going to go through all 4 of them, but for example, if we wanted to look at the tangent function, all we need to know is what happens with sine and cosine. So if I define h of t to be tangent of t, and I want to determine is tangent even or odd, I would plug negative t into that function and then try and simplify it. H of negative t would equal tangent of negative t by definition. But what is tangent? We have an identity that says that tangent of an angle is equal to sine of that angle over cosine of that angle. Sine of negative t over cosine of negative t. Now think about what we just figured out. Cosine of t is an even function, and even functions absorb those negatives. So cosine of negative t is the same thing as cosine of t. Sine is an odd function, and in odd functions, negatives can be pulled out. So the negative disappears for the cosine, but the negative for my sine function gets pulled out, and I can even bring it all the way out to the front of the fraction the way I did here. Now I have negative sine of t over cosine of t. Ignoring the negative for a second, sine over cosine is tangent, and this negative out front is going to make this a negative tangent of t, which is the same thing as negative h of t. From here to here, we see that tangent is an odd function. I could do a similar derivation for the other 3 trig functions, but instead I'm going to just list them right here. So what we're seeing is that cosine and secant are even functions. And remember, this is the case because secant is the reciprocal of cosine. Remember, taking the reciprocal of a function doesn't change its sign. So if cosine is even, its reciprocal would have to be even as well. Sine and tangent, we just determined, are both odd, so their reciprocals, cosecant and cotangent, would also be odd. Notice that most of the trig functions are odd, only 2 of them are even. Okay? In the next video, we'll do an example where we can use this identity.